Okay, so welcome everybody. My name is Andreu Aliu and I'm an Erasmus student. I'm a student from Universitat de Girona in Spain, and I've been here at Odisee this semester, and I've been working on my bachelor thesis, working with the LoRe project, designing a robot. So first, let's take a look about what the LoRe project is. It began in January 2020, and its aim was for providing students an opportunity to engage with 3D printing and sheet metal projects. The goal was to have students focus on the mechanical parts of the robots, while the professors take care of the electronics and software parts. The first robot that was developed was the LoRe development prototype. Its goal was to experiment and try for the electronics and software parts that was being used for the rest of the robots. Then the first ones were the Ticinator for welding and the Massebox that was designed but never built. Later they came the Bastet and La Ragna that they were inspired on a shape of a cat and a spider respectively. All of those robots were powered by Tisco. That's a firmware and control software that is being developed by Jürgen. Tisco, it's built and based on Arduino, and it works with COSMOS OpenC3 software that facilitates the control and communication with a computer. Currently, this setup is capable of driving up to 16 modified hobby servos and getting the input positions from different potentiometers. Now let's look into the robot that I've been working on. La Ragna is a 4-leg robot. Each leg consists of 3 different parts. There's the hip, the thigh, and the shin. In order to move the center of mass close to the body, all of these servos have been moved to the side in a way that the shin servo has to use a belt to move the joint. The majority of the parts are made from plastic, but as the project goal is to experiment with sheet metal, the legs had to be built from this material. The first La Ragna started in February 2022, and it was designed by Julie and Apollo in the course Design 4. Next year, those same 2 students built its robot in the course of Project 3. This was the second version. Simultaneously, other students were given the screenshots and assembly files from the version 1, and they were asked to modify it and improve it. At this point is when I came along. My project is to build on top of version 2, first identify the problems that it has, redesign it, and then build it. So on my design, at the start of the project, I established with my professor Jürgen the requirements that I had to accomplish. First, not to rely on the servo limits. So each mechanical part had to have hard stops that limit the movement. Bearings were mandatory to be used. To use as few screws as possible. The robot leg had to keep its integrity when the servos were removed. Also, to have a good cable management, the range of motion had to be, for each joint, the one specified. And the shin to thigh ratio must be the golden ratio of 1.6 to have lots of holes, so the design is flexible, and lots of things can be attached to the leg for future applications. And on this version, the belt must be straight. My first task was to study the problems on the version 2. So, for example, the hip joint here has a lot of range of motion on one side, but not as much on the other. That's because the servo is colliding with a column in the structure. Also, in the thigh makes contact with the base part here, and they even had to cut a part of the model so the leg can have a full range of motion. Here, as I mentioned, the range of motion is not symmetric on the hip, and also the angles are not the ones required. About the belt, in their design was twisted like that. This creates lots of on-the-side stresses on the belt. Also, there are problems because the belt makes contact with the structure, thus causing it to be damaged. And also, the step size of the belt doesn't match the gears one. The tie joint is held on one side with a bearing, and on the other side with the servo, thus creating that the servo is carrying much of the load of the leg and causing it to potentially be damaged. Cable management here, as you can see, some cables are getting pinched in a joint. For the servo holdings, in the construction phase, they had to use zip ties, glue, and metal pins that were required to securely hold the servos, creating challenges when new replacements had to be put. On the dimensions, first, as you can see here, the leg is not quite aligned with its axis of movement. Also, the body of the spider was too large, and the thigh-to-shin ratio was not the golden ratio that was required. On the structure, for attaching the leg to the main body, they used these thin slots that were very difficult to print on the 3D printers, and they were also not very strong. They could easily break. So having seen all these problems on the previous version, I was ready to think on my design. My first approach was to think on the joints. The easiest way is to put the servo like that to connect the two parts, but this is not very good, as if we take the servo out, the joint just disassembles. So the next obvious move is to put a bearing here that can hold the two parts connected when the servo is removed. And finally, I ended up with a design like this that has two bearings and the servo that slides in place, engaging with the joint and being capable of driving it. So this joint design can be integrated in various different configurations that I had to consider. And another thing to mention is that the servo is held in place with snap clips like that. So the previous design used a twisted belt, as I mentioned, that we want to remove. So in my design, I decided to put it underneath the leg. And in order to transmit the power from the servo to the gear, we had to use a gear system like that. Before starting with the first design, I need to calibrate the 3D printer to get to know the tolerances that it has. So I designed some test prints to calibrate for that. For example, for the shaft axis, there was this part built where you can find the exact hole diameter. Also, I designed one for the bearings that uses circlips to be retained. For the servo enclosures, so the servo has to be fixed in the position and not be loose. Here you can see the joint that I showed you before. The snap fits to get to know the elasticity of the plastic, and a belt gear, because I have to calibrate to get to know the exact step size and diameter to use. So getting to the correct design is an iterative process. In this case, it took me 4 iterations to get to the last design. The first one used very rough shapes, and it was more of a proof of concept. In this phase, I didn't build the metal parts. Then in the next version, I solved some of the major problems. Here I also introduced this curved shin part that resembles more of a spider, and also it can get to a more closer angle. The third and fourth versions were to solve minor mistakes. And here was also where I introduced the body of the robot. Throughout this iterative process, I encountered some problems that I now want to share with you. So the first one was that in the first design, the servo was mounted in a way that the snap fin clips were handling much of the torque load of the servo. This was not very good because these parts were were not designed to handle very big stress. So in the next iteration, I changed the direction of mounting the servo. So the walls now hold all the torque. Also, in the first design, I had this, the belt gear was between two very separated walls. And as this part has to handle out all the tension from the belt, it was very easy that it could break. So in the next version, I moved this wall to the other side of the gears, so the space is smaller. Another problem that I had was that the belt gear slipped on its axis. That was a metal pin. So my approach was to grind the metal pins so they can fit perfectly on the gear. But this didn't fully solve the problem, as the plastic around the pins got damaged and had a lot of play. So in my last version, I changed the material for printing the gears. I used carbon fiber reinforced nylon that is a lot stronger, a lot harder, and it doesn't get damaged that easily. One problem that persisted throughout the iterative process was the play in the joints. So the solution here was simply to get to the correct dimensions, to the correct size, that was at the same time a tight fit and was easy to mount. Also, some snap fin clips had to be changed to have to better mount, better hold on the servos. So my final result is version 4.4. Here you can see a render of the whole robot. And so for the construction of the robot, different techniques were used, such as 3D printing for the plastic parts, laser cutting for the structures and different pedestals. Also for the metal sheet I used a water jet and the bending machine. And for for modifying the metal pins, I used the grinding tools, and I even used a custom-made tool that I designed to cut the belt in the exact width. Also, as a side project, I built a joystick that resembles the shape of the robot. Here, those are potentiometers that are connected to the board and can drive each servo. So thank you for listening, and we will try to show you a little demo of the robot now. And after that, I'm pleased to receive any questions that you may have. Yeah. So here you can see the last version that is controlled by the Tisco board that is connected to the platform, to the computer, and it's communicating with the COSMOS interface. The robot, it moves. Here you can see the control interface. So it can be moved. You can move each servo individually. And yeah, we also record. You can record a movement here and play it back later.
Can you put it in place?
Yeah. So here the robot is playing back a motion that we recorded. That's, for instance, the logo of my school. And As you can see, it's a bit wiggly, but can you repeat the same or the other one? Yeah.
It's the same speed, I forgot to say it. It's 2 seconds.
So it goes through the exact same positions now. Do you want to try with the joystick?
I'm going to do higher speed first.
Okay.
But I forget. So first motion and then attach?
Yes. Yeah, I think you have to do attached last.
This is fast.
You can change the speed.
Oh, delete.
Yeah. There's also, so you can program different motions of it on it, and it also can use a joystick to be moved.
Yeah, after I'm going to put it in a safe position. Alright.
So, well, this is, should move that. The joystick, it's now glued to the table. But as you can see, with x-axis, you can control one or the other servos. We also built, as I told you, this other servo, but it has to be calibrated, so we haven't already tried it. But it's it's the same, just with these potentiometers. If you want, you can play with it, or if you want to check the other versions that I built and see how they are built, you can also check this out. Yep. Yes. So, for instance, this was the version that the other students built. This is the first one, the development prototype. This was the first that I showed you all the different weaknesses and problems that it has. And this is, I think, the version 2, version 3, and the last, the version 4.
That's probably easier.
Yeah. Closer.
Yes. It can touch it.
So what changed between this version and this one was modifying changing the materials of the gear, and also some changes in the base, and to make it tighter, so the servos fit.
Push down on the no.
Oh.
Weight, because we don't have a weight.
Oh, okay, yeah. I restarted it.
That's no problem.
So then if you want to check this one, it's the latest version. This is the OPT logo.
Yeah, it's double speed. Like repeatability is very good. It looks bad, but it's just the artifact of the recording. These are low cost speakers that are inside, but it goes exactly to the same position, which is important for the mechanical properties of the car.
Yep.
What improvements do you suggest for, let's say, version 5? So what comes next?
Yes.
What change for a new student or a new group for the future?
Yes, so for example, problems that I have with this version, one problem is that the belt, there's no way to tighten it up when it's already mounted. So you have to make a lot of force when mounting it, but then if it gets loose over time. So an improvement would be to make a system with a screw or something like that that can tension the belt, maybe controlling the distance between the thigh part. Another improvement maybe it's to redesign the parts in a way that they're geometrically more efficient. For example, studying with the loads that the leg has, the best geometry with generative design. Geometry optimization. Yeah, well, I have a little slide to show that. I think, well, maybe not. Yeah, so these are the two. So topology optimization is a technique that uses software to calculate where which parts of the structure are most necessary to carry the load. So designing the whole structure with that would make an improvement because it will make the robot lighter and maybe stronger at some parts.
Impossible to do.
Yeah.
No more questions.
We have seen the robot do some movements that are not wanted, I suppose. It hits the table, for example. So is it possible to define a kind of safety zone if you move the joystick that the robot
yes.
does not go further when there is a table?
Yeah, of course. So now the robot, this is a software part, might go mechanical part, but now the robot, it's controlled only by moving the servos, just sending the values of the servos, and also for the movements to play the servos that you record moving the leg. But a further improvement would be to make, that would be a software improvement, would be to make to calculate inverse kinematics, so calculate its position in the three-dimensional space of the tip. So with that, you could calculate where the surface is, and you could make, for example, a safety box around it, so it doesn't move further of this zone. Yeah, but that would be, you had to do this in software, and you had then to calculate the position of the tip mathematically in the 3D space.
Which industry can use that in the future?
Sorry?
Which industry can use that in the future?
Well, this robot, at the end, it will be a robot that's capable of walking. So maybe for exploration or something like that. But the most important part is that with that, you can learn a lot about how an arm moves. And the arm, it could be implemented in a lot of industries for manufacturing and automating any kind of process that needed, like a moving arm to position things, maybe welding. For example, the first robot that was built, its goal was to be a robot hand that could weld. So, yeah, for the leg, they had a lot of applications. For the whole robot, it will be something more like exploration or something like that.
And it's designed to have 4 arms, or?
Yes, the robot is designed to have 4 arms, but my work was, because it will be further improved, so it was just a proof of concept, or how to improve just 1 leg.
Have you any solution about the movements? Will you, the movements are a little bit...
Yeah, that,
Smoother.
so,
Smoother, yes. Because when you will to use this one to a weld.
yeah, of course it
The
it won't be.
movements
So there are 2 parts here. So there's the software part. So maybe make on the software, send the values of the servo not directly the position, but because like a smooth function or something like that. But on the mechanical parts, that was my goal here. Yeah, a lot could be improved. The servos have a little bit of play, and also the structure has some play. So maybe, so that's a problem that I encountered a lot during the whole iterative process. That I had to calibrate for all the joints to be tight enough that they're easy to mount and dismount. So you can take the servos very easily. But then it has to be tight enough that there's no play between the parts. But this is plastic, so it's a bit elastic. Maybe if you build it with stronger servos and all made of harder parts, harder materials like metal, or maybe you could try with, I don't know, other types of plastic. So the parts are more consistent and stronger. I think that would solve the problem.
Bit heavier.
Yeah, then it will be a lot heavier, so you'll need beefier servos.
Okay.
Mm-hmm.
Thank you.
Any other question? Maybe if you I want you to try it to move or something.
No, I think they are happy with the movements they saw.
Yeah.
We'll do that when we stop recording.
Okay, now for the
So
difficult questions, we will shut down the video. Okay, thanks very much.
Yeah, thank you everybody for listening.
Were you pleased with your stay here in Odisee?
Yes, I was very pleased. I liked a lot because here in this university you work a lot more on the practical aspects.